Memory management is one of the most important aspects of programming in general, but it is also a little tricky to get a hold of sometimes. So tricky in fact that once we figured out how to do garbage collectors properly we never came back. In this video I'm going to focus on the manually managed languages, the whole 2 of them, and walk you through the various memory allocation techniques. Although memory allocation may seem like an operating system exclusive type of thing, the reality is that any program can implement its own memory allocation for internal use. For example, let's take a look at malloc from the C standard library. Okay, maybe it's a bit too long, but the gist of it is that malloc keeps track of free spaces of memory in blocks and returns a pointer to one of these blocks when requested. There's little influence by the operating system when using malloc. It's only when you deplete the heap that malloc actually solicits more memory to the OS, but before that, you're just using the pre-allocated memory for the program. Additionally, freeing memory doesn't actually return that memory to the operating system. It adds that block of memory to a free list, which is the first place malloc looks for when allocating memory. The free list is usually a circular list of memory chunks with administrative data at the beginning. This is also the reason why managing small memory elements is inefficient, as it creates fragmentation in the free list. Knowing all of this, then why should you care about managing your own memory when malloc is already doing it for you? Malloc is a general purpose allocator, which makes it not as efficient as it could be for some cases. It also becomes super slow when requesting more memory from the kernel. But fear not, there exists a solution to all of this. The bump allocator is the fastest allocator there is. It's just a block of memory of a certain size with a pointer to the next free space. When you allocate something, that pointer is returned to you and the internal pointer of the bump allocator advances by the size of the element, so there's pretty much no overhead when allocating. Deallocation of single elements is not possible. You're only able to deallocate the whole block by returning the pointer to the start. It's pretty good for game that when you need to allocate things that only last for a frame or so, then deallocate the whole block and start over again. Slab allocators are another useful type of allocator that, unlike bump allocators, actually do support freeing of elements. Quoting the article where I got the idea for this video, a slab allocator is literally just a fucking array with a singly linked list pointing at the next free item. The downside of this array-like structure is the limitation of only holding one kind of object, so it's not general purpose. This allocator is pretty good for object pooling, where you have a cache of elements ready to be used at any one time. You can also fancy this up by managing an extra linked list to point at other available slabs in memory so that you can dynamically shrink or grow the total object pool size. The body allocation technique is an algorithm that divides memory into partitions to try and satisfy a request as suitably as possible. It's based on binary trees and its name comes from the fact that all memory chunks have a body. This allocator is generally used for embedded applications as it's pretty flexible and doesn't require all that much metadata to maintain. Let's take a look at a simple example. Say you have a block of memory of 256 bytes and your minimum allocation size is 32 bytes, so you're able to allocate blocks of 32, 64, and 128 bytes. You're gonna need a free list for each one of the possible allocation sizes. The difference in exponent in both limits is the number of free lists for that body allocator. In this case, it's 3. We also need a way to store the state of each memory chunk in the allocator. A chunk of memory is unused when neither of its children are being occupied. It's considered used if both are occupied and split if only one of them is. If you think about it, an unused memory block will always be contiguous and will be stored in its corresponding free list, whilst a used block is of no value to the allocator. We only need to know if a memory chunk is split so that we can merge it with its body when freeing memory. Instead of implementing a binary tree only to store a boolean, we can use a bit field as a linearized binary tree to indicate if a certain node is split or not. Here are the arithmetic operations used to traverse the linearized binary tree. Lastly, when you give out a memory block, you need to store the order of that block in the first byte so that you can free it properly later. Let's allocate a 10 byte block. We need at least 11 bytes of memory to satisfy this request. The closest power of 2 we've got available is a 32 byte block, so we try to pop a block off the 32-byte free list. If there are no free blocks available, we travel up the tree until we find any available block. When we find an unused block, then we only need to divide it until we get to the desired order, making sure to flip the isSplit flag of the linearized binary tree every step of the way. This way we also get a free block for every power of 2 we had to split. If we now wanted to allocate a 60-byte element, we will just take the available block in the free list and be done there and then. The biggest drawback of body allocators is that they suffer from internal memory fragmentation, so you'll also need to implement a memory compaction system with a reference to all the pointers you've given out. Although I mainly focus on the last 3 allocators, there are way more out there that are in some ways based on the ones I covered. For example, a stack allocator is just a pump allocator, but you can pop elements off the top, and a weighted body allocator is just harder to look at. There's also the free list allocator, which is the same technique malloc uses to manage its memory. I didn't go too in depth to talk about it because I felt like I would kinda be repeating myself a bit, but other implementations of user space free lists were considerably faster than malloc, so you get the idea. Here are the benchmarks of the little implementations I did for each of the 3 allocators. You can clearly see malloc is the slowest because of its generalist nature and has that linear time complexity. Both bump and slap allocators are in constant time and are pretty fast, whilst the body allocator's time complexity is logarithmic, so you can kinda see it growing at the end there. My biggest piece of advice would be to avoid dynamic memory allocation as much as possible. If you already know how many elements you're gonna need, then just implement a static array and be done with it. Only consider using dynamic memory in cases where the user has a lot of influence over the program's execution and memory usage. If you're worried about performance and you're employing dynamic allocation, then you should consider using a custom allocator over malloc, taking into account the lifetimes and data of your elements to choose the right fit for your application. There is also the whole other topic about memory alignment, but I didn't allocate enough time for this video.